Hello, friend. If you're here, it means the day has quieted, the rush has slowed, and somewhere in the stillness you looked up, maybe through a window, maybe in your mind, and wondered about the stars. Tonight, we're going to talk about something small, something ancient, something you've seen 1,000 times but never quite understood. Why do stars flicker? It's a question older than telescopes, older than cities. A question asked by shepherds in deserts, sailors on dark oceans, children lying in grass, staring up at a sky too big to name. And the answer? It's quieter than you think, softer, more beautiful. Because stars don't really flicker at all. Before we drift into this, I want to say something. If you're here for the first time, or if you've been here before and these quiet nights bring you comfort, you're welcome to stay. You might like to gently tap the like button, not because I ask, but because it tells the algorithm that slowness still matters. You can subscribe if you'd like more of these soft journeys, and ring the bell not for noise, but so the next quiet night can find you again when you need it. No pressure, no urgency, just an invitation. Now, let's drift. Imagine this. You're standing outside. The air is cool. The sky is clear. Above you, scattered like salt across black cloth, are thousands of stars. And if you watch them long enough, really watch, you'll notice something strange. They shimmer. They pulse. They seem to breathe. Some flicker fast like candle flames in wind. Others glow steady for a moment, then tremble, then steady again. A few seem to dance, shifting colors, red to white to blue, as if the sky itself is alive. It's hypnotic. It's ancient. And for most of human history, no one knew why. The Greeks thought stars were holes in the fabric of heaven, letting divine light leak through. Medieval monks believed the shimmer was angels singing their voices made visible. Sailors called it the winking of the drowned, a superstition born from too many nights at sea. But here's the truth whispered by science and told softly. Stars don't flicker because they're unstable. They don't pulse because they're dying. They shimmer because of us, because of where we stand, because of the invisible ocean between us and them. Tonight we're going to take a journey. Not through space, though we'll touch it. Not through time, though we'll feel it. We're going to walk through light, through air, through the strange, beautiful accident of perception that makes distant suns look like they're trembling just for you. You don't need to understand everything. You don't need to remember the formulas or the names. You just need to rest, breathe, and let starlight do the teaching. Because this story, this answer to why stars flicker, isn't just about physics. It's about distance, about atmosphere, about the way our eyes hold light before letting it go. It's about standing on a spinning rock, wrapped in a blanket of gas, looking out at fires, burning trillions of miles away, and somehow impossibly feeling connected to them. So let's begin where all light begins. Not in your eyes, not in the sky, but out there, in the furnace of a star. Every photon of starlight you see tonight started its journey a long, long time ago. The closest star to Earth besides our sun is called Proxima Centauri. It's a small, dim, red dwarf star barely visible even with a telescope. And it's 424 light-years away. That means the light you see from Proxima Centauri tonight left that star over 4 years ago. When that photon began its journey, you were younger. The world was different. Maybe you were in a different place, living a different life. And yet, that particle of light traveling at 300,000 kilometers per second, the fastest speed in the universe, has been moving through the void in total silence, in total darkness, just to reach your eyes tonight. 4 years. For the closest star. Now imagine the others. Sirius, the brightest star in the night sky, is 8.6 light-years away. The light you see from Sirius left when you were even younger still. Betelgeuse, that red giant in the shoulder of Orion, is roughly 640 light-years away. The light touching your eyes right now left Betelgeuse in the year 1384 before Columbus sailed, before the printing press, before the Renaissance. And those are just the neighbors. Some stars you see tonight are thousands of light-years away, tens of thousands. And a few, those faint, barely there pinpricks at the edge of vision, are so distant that their light has been traveling since before human beings learned to speak. You're not looking at the present. You're looking at the past, at ghosts, at echoes. Every star you see is a time capsule frozen mid-burn, sending its light across the void, like a message in a bottle, hoping without knowing that someone somewhere will see it. And you do. But here's the strange part. That light, traveling for years, for centuries, for millennia, arrives at Earth almost perfectly. It crosses the emptiness of space without bending, without breaking, without fading into nothing. Space, after all, is a vacuum. There's no air, no dust, no interference, just pure, unbroken dark. And in that dark, light travels in straight lines, steady, predictable, constant. If you were floating in space far from any planet and you looked at a star, you'd see it perfectly still. No shimmer, no flicker. Just a hard, bright point, burning cold and clear against the black. Astronauts on the International Space Station see stars this way. So did the Apollo astronauts on the moon. In every video they took, every photograph, the stars look sharp, frozen, eternal. Because out there, there's nothing in the way. But down here, there's us, and the ocean we live in. You probably don't think of it this way, but you're standing at the bottom of an ocean right now. Not water, not liquid, air. The Earth's atmosphere, the blanket of gas wrapped around the planet, stretches about 100 kilometers above your head. It's thick at the bottom where you stand and thins as it rises, fading slowly into space. And this ocean, it's not calm. It churns, it shifts, it breathes. Temperature changes from layer to layer. Pressure rises and falls. Humidity drifts in invisible currents. Wind moves at different speeds depending on altitude. Even on the stillest night when the air feels frozen, the atmosphere above you is in constant motion, rolling, mixing, colliding. And every time a beam of starlight enters this invisible ocean, something happens. It bends. The scientific word is refraction. When light passes from one medium to another, say from the vacuum of space into the gases of Earth's atmosphere, it changes speed. And when light changes speed, it changes direction. You've seen this before, even if you didn't notice. Put a straw in a glass of water. Look at it from the side. The straw appears to bend at the surface as if it's broken. That's refraction light bending as it moves from air into water. Or imagine driving on a hot summer day. You see that shimmer on the road ahead, the mirage that looks like water. That's refraction, too light bending through layers of hot and cool air near the pavement. The same thing happens with starlight. As light from a distant star enters Earth's atmosphere, it passes through layers of air with different temperatures, different densities, different pressures. And each time it crosses a boundary between these layers, it bends. Just a little. Just enough. And because the atmosphere is always moving, always shifting, those bends change. Constantly. One moment the light bends left. The next, it bends right, then up, then down. To your eye standing at the bottom of this ocean, the star appears to move. It doesn't, of course. The star is millions of miles away, burning steady and still. But its light is trembling. Some nights are worse than others. On cold winter nights, when the air is sharp and dry, stars flicker wildly. That's because cold air is denser than warm air, and the boundary between them is sharper. Light bends more dramatically at those sharp boundaries. On humid summer nights, the air is thicker, softer. Stars still shimmer, but slower, gentler. And on nights when the atmosphere is very still, when there's no wind, no weather, no movement, the stars almost stop flickering entirely. They glow steady and calm, as if the sky has finally exhaled. But those nights are rare. Most nights the air is restless, and so the stars shimmer. Now here's something strange. If you've ever looked at planets Venus, Mars, Jupiter, you might have noticed they don't flicker the same way stars do. Why? Because they're closer. A star, even a relatively close one, is so far away that it appears as a single point of light. All the light from that star is focused into one tiny dot. So when the atmosphere bends that light, the entire dot moves, flickers, trembles. But a planet, is close enough, at least cosmically speaking, that it appears as a disk. A tiny disk, yes, invisible to the naked eye, but a disk nonetheless. And because it's a disk made of many points of light, the atmospheric bending averages out. Some light bends left, some bends right, some bends up, some bends down. The result, planets glow steady. It's one of the oldest tricks in astronomy. Ancient observers didn't have telescopes, but they knew if it flickers, it's a star. If it doesn't, it's a planet. They called planets wanderers because they moved slowly across the sky. But they could have just as easily called them the still ones. So here we are, standing at the bottom of an invisible ocean, looking up at lights that traveled for years, sometimes centuries, to reach us. And just before they arrive, just before they touch our eyes, they pass through this churning, breathing atmosphere. And they shimmer. Not because they're unstable, not because they're dying, but because the air between us and them is alive. Because the universe in its own quiet way is showing us something true. Nothing travels untouched. Even light, the fastest, most eternal thing we know, bends under the weight of the world. And maybe that's okay. Maybe the shimmer isn't a flaw. Maybe it's a reminder. A reminder that we live here wrapped in air, protected by this fragile blanket of gas. A reminder that the stars, for all their distance, are still connected to us, that their light, ancient and tired, still finds a way to tremble when it touches home. You don't have to understand the physics perfectly. You don't have to remember the names, refraction, scintillation, atmospheric turbulence. You just have to know this: the stars are still. But the sky breathes, and in that breath, light dances, and tonight, as you drift towards sleep, you can close your eyes and know somewhere above you, invisible and endless, that dance continues. For you, for everyone, for no one, just light, just air, just the quiet motion of a universe that doesn't need to be understood, only felt. So what happens when we look closer at this invisible ocean? When we follow the light deeper into the layers, into the turbulence, into the science that makes the shimmer real, that's where we're going next. Into the currents, the winds, the hidden forces that make stars tremble in the dark. The light touches your eye in an instant. But it didn't start there. It started impossibly far away, in a place you'll never visit at a time you can't imagine. And it traveled alone, silent, patient, across distances so vast that even numbers stop making sense. Tonight, we're going to follow that journey. Not all of it that would take lifetimes, but enough to understand what it means when you look up and see a star. Enough to realize you're not just seeing light, you're seeing time. Let's start with the nearest star. Not the sun that's too close, too familiar. Let's talk about the next one. The one after our own, Proxima Centauri. It's a small star, a red dwarf barely glowing tucked into a triple star system in the southern sky. If you were standing in the right part of the world with a telescope, you could just barely see it, a faint red dot easy to miss. But here's what makes it extraordinary. It's 4.24 light-years away. That means the light you see from Proxima Centauri tonight, right now in this moment, left that star 4.24 years ago. Think about that. 4 years ago, where were you? What were you doing? Who were you becoming? That photon of light, the one about to enter your eye, was already on its way. It left Proxima Centauri when you were younger, when the world was different, and it's been traveling ever since. Through the void, through nothing, at 300,000 kilometers per second, for 4 years, and it finally arrives tonight, just in time for you to see it. Now, 424 light-years might not sound like much. After all, it's the closest star, practically a neighbor. But let's put that distance into perspective. If you could travel at the speed of a commercial airplane, about 900 kilometers per hour, it would take you over 5 million years to reach Proxima Centauri. If you could travel at the speed of the fastest spacecraft humanity has ever built, the Parker Solar Probe, moving at about 700,000 kilometers per hour, it would still take over 6,000 years. Even light, the fastest thing in the universe, takes over 4 years. Space isn't just big, it's incomprehensibly, impossibly, brutally empty. And yet somehow light crosses it, every night, without fail, without sound, without pause. But Proxima Centauri is just the beginning. Look a little farther. Look at Sirius. Sirius is the brightest star in the night sky. It's hard to miss, blazing white and blue, often mistaken for a plane or a satellite because of how intensely it shines. Ancient Egyptians based their calendar on Sirius. They called it the Nile Star because its rising marked the annual flooding of the river. Sirius is 8.6 light-years away. The light you see from Sirius left that star in 2016. Think back. 2016. Where were you? What was happening in the world? What songs were playing? What headlines were breaking? That light was already traveling, already moving through the dark, already on its way to you. And it's arriving now, tonight, in this quiet moment. You're not looking at Sirius as it is. You're looking at Sirius as it was almost a decade ago. Let's go farther. Look at Betelgeuse, that massive red swollen giant in the constellation Orion. It's one of the most famous stars in the sky, visible to the naked eye even from cities. Astronomers love it because it's unstable pulsing, nearing the end of its life. Betelgeuse is roughly 640 light-years away. The light you see tonight left Betelgeuse in the year 1384. Let that settle in for a moment. The Renaissance hadn't started yet. Gutenberg hadn't invented the printing press. Columbus hadn't sailed. Shakespeare hadn't been born. The world was smaller, quieter, slower. And in that year, 640 years ago, a photon of light left the surface of Betelgeuse and began its journey through the void. It's been traveling ever since. Through centuries, through wars, through the rise and fall of empires, through the invention of electricity, the airplane, the internet. And tonight, it arrives. It touches your eye, and you see it. Not as it is now, as it was then. Here's the strange, haunting truth: Betelgeuse might already be dead. Astronomers have been watching it closely for years. It's a supergiant star, unstable and bloated, nearing the end of its life. At some point, maybe tomorrow, maybe in 100,000 years, it's going to explode in a supernova, one of the most violent events in the universe. But if that explosion happened 500 years ago, we wouldn't know yet. Because the light from that explosion is still traveling, still crossing the 640 light-years between Betelgeuse and Earth. We could be looking at a ghost, a star that no longer exists, still shining in the sky because its final light hasn't reached us yet. And when it does, when that supernova light finally arrives, it will be bright. Brighter than the full moon, visible during the day. A new star appearing suddenly in the sky, blazing for weeks before fading. But it won't be new. It will be old, ancient. A message from the past delivered late. Every star you see is like this. A time capsule, a memory, a photograph taken years, sometimes centuries, sometimes millennia ago. The stars aren't showing you the universe as it is. They're showing you the universe as it was. And the farther you look, the deeper into the past you see. Look at the stars in the Big Dipper. That familiar pattern, the one humans have used for navigation for thousands of years. The closest star in the Big Dipper, Megrez, is about 80 light-years away. The farthest Alkaid is roughly 100 light-years away. The light from those stars left before your grandparents were born, before World War II, before the invention of the radio. And yet there they are, still forming the same shape, still guiding travelers, still hanging in the sky like they always have. Or look at Polaris, the North Star, the one sailors used to navigate the one escaping slaves followed to freedom. Polaris is 430 light-years away. The light you see tonight left that star in the year 1594. Shakespeare was 30 years old. Galileo hadn't yet turned his telescope toward the heavens. The scientific revolution was just beginning. And now that light traveling for over 400 years finds you. But let's go even farther. Let's talk about stars so distant, so faint, that you can barely see them. Stars at the edge of naked eye visibility, hovering just above the horizon on the clearest nights. Some of those stars are 1,000 light-years away. 2,000, 5,000, the light from those stars left during the Middle Ages, during the Roman Empire, during the Bronze Age. Some of the faintest stars you can see, if you're in a place dark enough far from city lights, sent their light toward Earth before humans invented writing, before we had language, before we had names for things. And still impossibly, that light kept moving, kept traveling, kept crossing the void without knowing if anyone would be there to see it. Now here's the question you might be asking: if light takes so long to travel, how do we even see it? Why doesn't it fade? Why doesn't it weaken? Why doesn't it disappear into the dark? And the answer is one of the most beautiful things about light. It doesn't get tired. Light doesn't slow down. It doesn't lose energy as it moves through space. It just keeps going at exactly the same speed forever until it hits something. A photon that left a star 10,000 years ago is moving just as fast and carrying just as much energy as a photon that left 1 second ago. Space doesn't drain it. Distance doesn't weaken it. The void doesn't swallow it. Light is patient. Light is eternal. And that's why even after traveling for years, for centuries, it can still reach your eye and make you see. But here's the paradox. Light travels in straight lines. Perfect, unbroken, predictable lines. In the vacuum of space, nothing bends it. Nothing stops it. Nothing interferes. So why, after all that perfection, after all that time, after crossing trillions upon trillions of kilometers without a single mistake, why does it flicker when it finally arrives? The answer, as we've started to see, isn't in the star. It's not in the light. It's not even in space. It's in the last 100 kilometers. The final stretch. The very end of the journey. It's in our atmosphere. Imagine you're that photon. You've been traveling for 640 years. You've crossed 640 light years of emptiness. You've seen nothing, felt nothing. You've just been moving silent and alone through the dark. And then finally, you reach Earth. You enter the atmosphere. And suddenly, for the first time in 640 years, something touches you. Air, molecules of nitrogen, oxygen, water vapor, invisible, scattered, constantly moving. And as you pass through them, they bend you. Just a little. Just enough. You were traveling in a straight line, but now you're not. You wobble, you shift, you refract. And to the person standing on the ground looking up, you appear to flicker. After 640 years of perfection, you stumble in the last 100 kilometers. That's the tragedy and the beauty. Stars don't flicker because they're unstable. They flicker because we're in the way, because we live at the bottom of an ocean of air, because the atmosphere, the very thing that protects us, that lets us breathe, that makes life possible, also distorts the light from the stars. It's as if the universe is whispering to us, and the air is translating, and something gets lost in translation. But maybe that's okay. Maybe the flicker is part of the message. Maybe it's a reminder that nothing, not even light, not even something that traveled for centuries, arrives untouched. That everything, even the most eternal things, bends under the weight of the world. So when you look up tonight and you see a star shimmer, remember this: that light is older than you, older than your parents, maybe older than your country. It's been traveling through darkness, through silence, through the endless void, just to reach your eyes. And it almost made it perfectly. Almost. But then it touched the air, and it trembled. And that trembling, that's not a flaw. That's proof. Proof that the light is real. Proof that the journey is over. Proof that after all that time, after all that distance, it finally found home. But if the atmosphere bends light, if it distorts the stars, then what exactly is happening up there? What forces, what currents, what invisible motions are shaking the sky? That's where we turn next, into the turbulence, the winds, the hidden chaos that makes the stars dance. You're standing at the bottom of an ocean right now. Not water, not liquid. Something lighter, softer, invisible. Air. And this ocean, this blanket of gas wrapped around the planet, is deeper than you think. Stranger than you imagine. And it's the reason stars flicker. Because between you and the stars, there are 100 kilometers of atmosphere. And nothing that passes through it arrives the same. If you're here in the quiet, listening to this, maybe you're thinking about the sky differently now. About light, about time, about the distances we can't touch. And if these gentle drifts through science bring you peace, you're always welcome here. You can tap the like button if this feels like home. You can subscribe to let more quiet nights find you. And the bell, you can ring it softly, not for alerts, but so the next story knows where to land. No rush, no noise. Just an open door. Now, let's sink into the ocean. The Earth's atmosphere is about 100 kilometers thick. That's if you measure from sea level to the edge of space where the air finally thins into nothing. But it's not evenly spread. Most of the atmosphere, about 75% of it, is packed into the first 11 kilometers above your head. That's the layer we live in, the one we breathe, the one where clouds form and weather happens. It's called the troposphere, and it's chaos. Here's what most people don't realize. The air around you isn't still. Even on the calmest night when the wind has stopped and the trees are silent, the atmosphere is moving. Constantly. Invisibly. The air near the ground is warmer than the air higher up. Warm air rises, cool air sinks. Pockets of air with different temperatures, different pressures, different densities. They're all mixing, colliding, swirling. And every one of those pockets bends light differently. Think of it like this. Imagine you're standing in a swimming pool, looking up at the sky. The water is calm on the surface, but underneath, there are currents. Tiny movements. Shifts in temperature. Now imagine dropping a coin into the pool and watching it sink. As it falls, it doesn't fall in a straight line. It wobbles. It drifts. The water pushes it left, then right, then left again. That's what happens to starlight as it passes through the atmosphere. The light enters from space straight, clean, perfect. But as it moves through the layers of air, each layer bends it. Just a little. Just enough. And because the air is always moving, the bending changes. Constantly. Unpredictably. To your eye, the star appears to shimmer. The scientific term for this is refraction. It's the same principle that makes a straw look bent when you put it in a glass of water. Light travels at different speeds through different materials. When it crosses from one material to another, from air to water, from space to atmosphere, it changes direction. But here's the key. Light doesn't just bend once. It bends continuously. As starlight passes through the troposphere, it crosses dozens, maybe hundreds of invisible boundaries. Each one bends the light slightly differently. And because the air is turbulent, because it's always shifting, those boundaries are never in the same place twice. One moment the light bends one way, the next moment it bends another way, and the star flickers. Let's talk about temperature. The air at ground level is warmer than the air higher up. On average, the temperature drops about 6.5 degrees Celsius for every kilometer you rise. That might not sound like much, but it's enough. Warm air is less dense than cool air, and less dense air bends light less than dense air. So as a beam of starlight passes from the cold upper atmosphere down through the warmer lower atmosphere, it bends. Gradually, predictably. But the atmosphere doesn't change smoothly. There are pockets, layers, bubbles of warm air mixed with cool air. And each one refracts the light differently. Imagine driving on a hot summer day. You're on a long, flat road, and ahead of you the asphalt seems to shimmer. It looks wet, like there's water on the road. But when you get closer, the water disappears. That's a mirage. And it's caused by the same thing that makes stars flicker. Hot air near the pavement bends light from the sky downward, creating the illusion of water. Your brain interprets the bent light as a reflection, even though there's nothing there. The shimmer you see on the road, that's refraction in action. That's the air bending light because of temperature differences. Stars flicker for the same reason. Now let's talk about something subtle, something most people never think about. Humidity. The amount of water vapor in the air changes how light bends. Dry air and humid air have different densities, and because density affects refraction, the more water vapor in the air, the more the light bends. On a humid summer night, when the air feels thick and heavy, stars flicker more slowly. The light is bending through denser, wetter air, and the changes happen more gradually. On a dry winter night, when the air is crisp and clear, stars flicker faster. The air is thinner, the temperature gradients are sharper, and the light bends more erratically. It's subtle. But if you've ever noticed that stars seem to shimmer differently depending on the season, that's why. The sky itself is breathing, and the stars reflect that breath. Here's a question you might be asking: if the atmosphere is so turbulent, if it bends light so much, why don't planets flicker like stars? It's a good question, and the answer is surprisingly simple. Planets are closer. A star, even the closest star, is so far away that it appears as a single point of light. All the light from that star is focused into one tiny dot. So when the atmosphere bends, that light, the entire dot moves, and you see it as a flicker. But a planet is close enough that it appears as a disk. A tiny disk, yes. Too small for your naked eye to see. But your brain can sense the difference. Because the planet is a disk, it's made up of many points of light. And when the atmosphere bends those points, they don't all bend the same way. Some bend left, some bend right, some bend up, some bend down. The result, the bending averages out, and the planet glows steady. Ancient astronomers figured this out thousands of years ago. They didn't have telescopes, they didn't have lenses or instruments. They just had their eyes and the sky and time. And they noticed some lights in the sky flickered. Others didn't. The ones that flickered were called stars. The ones that didn't flicker were called planets wanderers, because they moved slowly across the sky over weeks and months. The Greeks used this to distinguish stars from planets. So did the Arabs, the Chinese, the Mayans. It was one of the first pieces of observational astronomy. A simple rule: if it flickers, it's far. If it doesn't, it's close. And it worked. For thousands of years. But here's something beautiful. Even though planets don't flicker like stars, they still shimmer. Just differently. If you've ever looked at Venus on a clear evening, that bright, steady evening star hanging low in the west, you might have noticed something strange. It doesn't twinkle. But it does seem to pulse, gently, subtly. That's because Venus is close enough to appear as a disk, but it's still far enough that the atmosphere affects it. The light from Venus is more stable than starlight, but it's not perfectly still. And if you watch Venus through binoculars or a small telescope on a turbulent night, you'll see it shimmer. The edges of the disk seem to ripple like looking at something through water. That's the atmosphere. That's the invisible ocean moving, breathing, bending light, even from the planets. Now let's talk about position. Not the position of the star, the position of you. Where you stand, where you look, changes how much stars flicker. If you look at a star directly overhead at the zenith, it flickers less. That's because the light is passing through the atmosphere at the shortest possible distance, straight down through about 100 kilometers of air. But if you look at a star near the horizon, it flickers wildly. Why? Because the light is coming in at an angle. It's passing through much more atmosphere, sometimes 30 or 40 times more before it reaches your eyes. Imagine looking through a window. If you look straight through, you see clearly. But if you look through the window at a steep angle, the glass distorts the view. You see reflections, warping strange colors. The same thing happens with the atmosphere. Stars near the horizon pass through more air, more turbulence, more temperature gradients, more humidity, and they flicker like crazy. That's why stars low on the horizon often appear to change color: red, then white, then blue, then red again. The atmosphere is splitting the light into its component colors like a prism. It's called atmospheric dispersion, and it's the same reason the sun looks red at sunset. Here's a common mistake people make. They think stars near the horizon are farther away. They're not. A star near the horizon is exactly as far away as that same star when it's overhead. The distance between you and the star hasn't changed, but the distance between you and the star's light has. Because the light is traveling through more atmosphere, it takes longer to reach you. Not much longer, maybe a fraction of a second. But that's enough for the turbulence to bend it more, to distort it, more to make it flicker more. It's not about the star. It's about the path the light takes. So here's what we know so far. Stars don't flicker because they're unstable. They flicker because the atmosphere, the invisible ocean we live in, is constantly moving. And as starlight passes through that ocean, it bends. Continuously. Unpredictably. The shimmer isn't in the stars. It's in the air. And the air is alive. It breathes. It churns. It shifts with temperature, with pressure, with humidity. And every shift, every breath, every tiny movement, it changes the path of light. It makes distant suns seem to tremble. But if you think about it, there's something poetic here. The atmosphere protects us. It gives us oxygen. It shields us from radiation. It keeps the planet warm enough for life. And yet it also hides the stars from us. It blurs them. It makes them flicker, shimmer, dance. We can't see the universe clearly because we live inside this blanket of air. But that's okay. Because the flicker, the shimmer, it's a reminder. A reminder that we're not floating in the void. That we're held protected, wrapped in something that keeps us alive. The stars flicker because we have an atmosphere. And we have an atmosphere because we have life. Maybe the shimmer is the price we pay for breathing, and maybe that's beautiful. Maybe it's enough to know that the stars are still out there burning steady and true, even if we can't see them perfectly. That the light is still traveling, still reaching us, still finding its way through the chaos. That even after crossing trillions of kilometers, even after bending and wobbling and trembling through the air, it still arrives. Still touches your eyes. Still makes you wonder. So if the atmosphere is the lens, constantly shifting, constantly bending light, then what exactly is moving up there? What invisible forces are churning the air, making the stars dance? We're about to step deeper into the turbulence, into the currents, into the hidden motions that shape everything you see in the night sky. The air above you is never still. Even now, even in this quiet moment, the atmosphere is moving, churning, colliding with itself in ways you can't see, can't feel, can't hear. And every one of those invisible motions changes the path of starlight. This is turbulence, the hidden dance. The reason stars don't just shimmer, they seem to breathe. We've talked about the atmosphere as an ocean, as a lens. But now we need to talk about what that ocean is doing. Because it's not calm, it's not smooth, It's a storm, slow, silent, and endless. And understanding that storm is understanding why some nights stars flicker wildly, and other nights they barely move at all. Let's start with something simple: heat. The sun warms the earth during the day, but it doesn't warm it evenly. Roads and cities absorb heat and radiate it back into the air. Forests and fields stay cooler. Mountains reflect sunlight differently than valleys. Lakes and oceans hold heat longer than land. And all of that uneven heating creates pockets of warm air and cool air scattered across the landscape. Warm air is lighter than cool air, so it rises. As it rises, cool air rushes in to take its place. And that movement, that circulation, is called convection. It's happening all the time. Even at night hours after the sun has set, the earth is still releasing heat, and the air is still moving. Now here's where it gets interesting. As warm air rises, it doesn't rise smoothly. It rises in bubbles, in pockets, in invisible columns called thermals. Pilots know about thermals, glider pilots especially. They ride thermals to stay aloft, circling inside these rising columns of warm air, climbing higher and higher without an engine. Birds know about thermals, too. Hawks, eagles, vultures, they soar inside thermals, wings spread barely flapping, just spiraling upward on invisible currents. But for starlight, thermals are chaos, because each thermal is a pocket of air with a different temperature, a different density, a different refractive index. And as starlight passes through one thermal, it bends one way. Then it hits another thermal, and it bends another way, then another, then another. The result, the star flickers. Not because the star is moving, but because the air between you and the star is a maze of invisible, shifting columns. Let's go higher. Above the surface, above the thermals, the atmosphere gets colder. Much colder. The temperature drops steadily as you climb about 6.5 degrees Celsius per kilometer. By the time you reach the top of the troposphere, about 11 kilometers up, the temperature is around 60 degrees Celsius. That's colder than Antarctica, colder than the coldest winter night you've ever felt. And that cold air, it's denser than the warm air below, much denser. So you have warm, light air at the bottom, cold, heavy air at the top, and in between a gradient, a slope, a constant shift from one state to another. And starlight has to pass through all of it. But the atmosphere isn't just layered vertically, it's also layered horizontally. Wind moves at different speeds at different altitudes. Near the ground, wind is slowed by friction trees, buildings, hills. It moves chaotically, swirling, changing direction. Higher up, wind moves faster, much faster. At about 10 kilometers above the Earth, there's a river of air called the jet stream. It flows from west to east, circling the planet, moving at speeds of 200 to 400 kilometers per hour, sometimes faster. The jet stream isn't a single smooth current. It meanders. It splits. It forms waves and eddies like a river flowing over rocks. And all of that movement, all of that turbulence affects starlight. Because as light passes through the jet stream, it's passing through air that's moving horizontally at hundreds of kilometers per hour. And that motion creates sheer layers of air sliding past each other, creating pockets of turbulence. And turbulence makes stars flicker wildly. Here's a way to visualize it. Imagine you're in a car driving at night. You're looking at the headlights of a car ahead of you. If the air is perfectly still, the headlights look steady. But if there's heat rising from the road, if there's a mirage, the headlights seem to shimmer. They flicker. They dance. That's turbulence. That's air moving, bending light, making distant sources of light appear unstable. Now imagine the car ahead of you is 640 light-years away, and the heat rising from the road is the entire atmosphere. That's what stars are dealing with. Here's something most people don't realize. Turbulence isn't just about big movements. It's about small ones too. Tiny eddies, microscopic swirls, pockets of air the size of your hand spinning, mixing, colliding. Scientists call this microturbulence. And it's everywhere. Even on the calmest night, even when the air feels perfectly still, there are tiny currents moving through the atmosphere. Invisible rivers flowing, churning, too small to feel, but large enough to bend light. And because these microturbulences are so small, they change fast. Very fast. That's why stars don't just flicker slowly. They flicker rapidly, sometimes several times per second. The light is passing through hundreds, maybe thousands of these tiny eddies, and each one bends the light slightly differently, constantly, unpredictably. To your eye, the star trembles. Now let's talk about seasons. You might have noticed stars flicker differently depending on the time of year. In winter, on cold, clear nights, stars seem to flicker wildly. They shimmer fast, changing color, dancing across the sky. In summer, on warm, humid nights, stars flicker more slowly, more gently, almost lazily. Why? Because the atmosphere behaves differently depending on the temperature. In winter, the air is cold and dry. The boundary between warm air near the ground and cold air above is sharp, very sharp. And sharp boundaries mean more refraction, more bending, more turbulence. In summer, the air is warm and humid. The boundary between layers is softer, gentler. The temperature gradient is more gradual, and gradual gradients mean less turbulence, less bending, steadier stars. So if you want to see stars at their most chaotic, their most flickering, go outside on a cold winter night. Look at the stars near the horizon. Watch them dance. If you want to see them at their calmest, go outside on a warm summer night. Look at the stars overhead. Watch them glow steady and soft. The stars haven't changed. The atmosphere has. Here's a question. Have you ever noticed stars flickering more on certain nights? Nights when the weather feels strange, when the air feels restless. That's turbulence. That's the atmosphere telling you it's moving even when you can't feel it. Let's talk about weather. Weather and turbulence are deeply connected. Before a storm, the atmosphere becomes unstable. Warm air is rising, cool air is sinking. Pressure systems are colliding, winds are shifting, and all of that instability creates turbulence. So if you go outside on a night before a storm, before the rain starts, before the clouds roll in, you'll notice the stars flickering more than usual. Wildly, erratically. That's the atmosphere preparing to erupt. Ancient sailors knew this. They used the stars to predict weather. If the stars were twinkling wildly, they knew a storm was coming. They didn't understand the physics. They didn't know about convection or refractive indices or microturbulence, but they understood the pattern. They understood that the sky in its own way was speaking, and they listened. Here's another common mistake. People assume that turbulence only happens during the day when the sun is heating the earth. But turbulence happens at night too. Even after the sun sets, the earth continues to release heat. Roads that were baked by the sun all day radiate warmth into the air. Buildings do the same. Lakes and oceans slowly cool, creating temperature gradients. And all of that creates convection, creates thermals, creates turbulence. In fact, some of the most beautiful star flickering happens in the hours just after sunset, when the earth is still warm, but the sky is already dark. The air is restless. The stars are trembling. It's chaos made visible. Now let's talk about altitude. The higher you go, the less turbulence there is. Near the ground, the air is thick, warm, and chaotic. But as you climb up a mountain, up in an airplane, up towards space, the air thins. The turbulence decreases. That's why astronomers build telescopes on mountaintops. Mauna Kea in Hawaii, the Atacama Desert in Chile, the Canary Islands, La Palma. These places are chosen not just because they're dark, not just because they're far from cities. They're chosen because they're above much of the atmosphere, above the turbulence. At 4,000 meters above sea level, about halfway up Mauna Kea, you're already above 40% of the atmosphere. The air is thinner. The turbulence is less. The stars flicker less. It's not perfect. You're still inside the atmosphere, still dealing with air, still dealing with some turbulence. But it's better. Much better. And the stars shine clearer, steadier, closer to how they really are. But even on a mountaintop, stars still flicker. Because you can't escape the atmosphere entirely, not unless you leave the planet. And that's exactly what astronomers did. In 1990, NASA launched the Hubble Space Telescope into orbit. Not on a mountain, not in an airplane, in space, above the atmosphere, above the turbulence, above all of it. And for the first time, humanity saw stars the way they really are. No flicker, no shimmer, no trembling. Just light. Pure, steady, unbroken. Hubble's images are sharper than anything taken from Earth. Not because Hubble is a better telescope, many ground-based telescopes are larger, more powerful. But because Hubble doesn't have to look through 100 kilometers of churning air. It sees the universe directly. And the stars, they don't flicker at all. So here's what we've learned. Stars flicker because the atmosphere is turbulent. And the atmosphere is turbulent because it's alive. Because it's warm and cool and moving and mixing and colliding with itself constantly, invisibly, without rest. Thermals rise. Jet streams flow. Micro-eddies spin. And every one of those motions bends light. Changes its path. Makes distant stars appear to tremble. It's not the stars. It's never the stars. It's the air. The invisible ocean. The blanket of gas that keeps us alive and hides the universe from us. But here's the beautiful part. That turbulence, that chaos is proof of something. Proof that we live on a planet with weather, with wind, with life. Dead planets don't have turbulence. They don't have atmospheres that churn and breathe and move. They don't make stars flicker. But we do. And maybe that's not a flaw. Maybe it's a gift. Because the flicker reminds us we're not looking at the stars from the void. We're looking at them from home, from a planet that breathes, from an atmosphere that protects us even as it blurs the view. So the next time you see a star flicker wildly trembling in the dark, remember it's not breaking. It's not unstable. It's just light passing through a storm too small to see. And that storm, that's the air. That's the wind. That's the invisible currents that make this planet alive. But turbulence is only part of the story. Because for centuries, scientists didn't have a name for this shimmer, this dance of light. And when they finally named it, they discovered something deeper, something about the limits of what we can see and how we've learned to see past them. For thousands of years, humans looked up and saw stars shimmer. And for thousands of years, no one knew why. They had theories, stories, guesses, but they didn't have the word that would turn a mystery into something measurable, something understood. That word is scintillation. And the journey to that word, the centuries of watching, wondering, testing, is a story about how we learn to see what's invisible. We've been talking about light, about turbulence, about the way air bends starlight into something that trembles. But now we're going to talk about the people who figured it out. The ones who looked at the flicker and refused to accept mystery as an answer. Because naming something doesn't make it less beautiful. It just makes it real. Let's go back, way back, to ancient Greece, to a man named Aristotle. Aristotle was a philosopher, a teacher, a student of everything. And one night, like everyone else, he looked up and noticed stars flicker. Planets don't. He wrote about it. He tried to explain it, and he got it wrong. Aristotle believed the shimmer came from our eyes. He thought that when we looked at something very small and very distant, our vision trembled. That the flicker wasn't in the stars, it was in us. He wasn't entirely wrong. Our eyes do play a role. But the main cause, he missed it. Because Aristotle didn't know about refraction. He didn't know about the atmosphere as a lens. He didn't have the tools to measure air, to understand its density, its motion. So he guessed. And his guess, like so many ancient guesses, became accepted truth for over 1,000 years. Fast forward to the 1600s, to a man named Isaac Newton. Newton was obsessed with light. He wanted to understand it completely, what it was, how it moved, why it behaved the way it did. He took a glass prism and held it up to sunlight, and he watched as the light split into a rainbow red, orange, yellow, green, blue, indigo, violet. 7 colors, separated, distinct. Newton called it a spectrum, and he realized white light isn't pure. It's a mixture, a blend of every color traveling together, only separated when something bends them differently. And that bending, he called it refraction. Newton didn't study stars directly, but his work on refraction, on how light bends when it passes from one material to another, laid the foundation. Because if light could be split by a prism, it could be split by air. And if it could be split by air, it could be bent by air. And if it could be bent by air in motion air that was constantly shifting, constantly changing, then maybe, just maybe, that explained the shimmer. But it wasn't until the 1800s that scientists really started paying attention. By then, telescopes had improved. Astronomers were building bigger lenses, better instruments, more precise measurements. And they kept running into the same problem. No matter how good their telescope was, stars still looked blurry, still flickered, still refused to come into perfect focus. At first they thought it was the telescope's fault. They blamed the glass, the mirrors, the alignment. But then they realized it wasn't the telescope. It was the air. The atmosphere was the problem. One astronomer, an Englishman named George Airy, spent years trying to measure the limits of telescopic resolution. How sharp could an image be? How small could a star appear? And he discovered there was a limit. Not because of the telescope, but because of turbulence. The air above the telescope was constantly moving, and that motion, those invisible currents, blurred everything. He called the effect atmospheric disturbance. We call it scintillation. The word itself comes from Latin. Scintilla. It means spark. A scintillation is a tiny flash, a brief shimmer, a spark of light that appears and disappears. It's a perfect word. because that's exactly what stars do when you watch them closely. They don't just flicker, they sparkle, they pulse. They seem to dim flash again, like sparks in the dark. By the late 1800s, astronomers had a name for it: stellar scintillation, the twinkling of stars caused by atmospheric turbulence. It wasn't magic. It wasn't divine. It wasn't a flaw in human vision. It was physics. But here's the thing about naming something. Once you name it, you can measure it. And once you can measure it, you can try to fix it. Astronomers realized if the atmosphere is the problem, then we need to either get above it or find a way to compensate for it. Getting above it. That took a while. We'll talk about that soon. But compensating for it, that started almost immediately. In the early 1900s, astronomers developed a new metric: seeing. Seeing is a measurement of how much the atmosphere distorts an image. It's measured in arc-seconds, tiny fractions of a degree. Good seeing means the air is calm, the stars are steady, images are sharp. Bad seeing means the air is turbulent, the stars are flickering wildly, images are blurry. On the best nights at the best observatories, seeing might be 0.5 arc-seconds. That's incredibly sharp, almost perfect. On bad nights, seeing can be 2 or 3 arc-seconds. Everything is blurred, distorted, unusable. Astronomers became obsessed with seeing. They built observatories in places with the best seeing: high mountains, dry deserts, remote islands. They tracked the weather. They measured humidity, wind speed, temperature gradients, all to minimize scintillation, all to see the stars as clearly as possible. But even with the best, seeing stars still flickered. So scientists tried something radical. In the 1950s, an astronomer named Horace Babcock proposed an idea. What if we could build a mirror that changed shape, a mirror that adjusted in real time to compensate for atmospheric turbulence? It sounded impossible. Mirrors are solid. They're fixed. They can't just shift. But Babcock believed it could be done. He called it adaptive optics, and it would take 40 years to make it work. Here's how adaptive optics works. You point a telescope at a star. The light from that star is distorted by the atmosphere, bent, wobbled, blurred. But instead of just accepting that distortion, you measure it. You use sensors to detect exactly how the light is being bent. Then, and this is the brilliant part, you bend the mirror to counteract it. If the atmosphere is bending the light left, you bend the mirror right. If the atmosphere is bending the light up, you bend the mirror down. You do this hundreds of times per second, constantly, automatically. And the result, the distortion cancels out. The image sharpens. The star stops flickering. It's like wearing glasses that adjust themselves constantly to correct for a blurry world. The first adaptive optic system was installed in the 1990s. At first, it barely worked. The mirrors were too slow. The sensors weren't sensitive enough. But over time, they got better. Much better. Today, almost every major telescope on Earth uses adaptive optics. The mirrors are made of hundreds of tiny segments, each one controlled by actuators, tiny motors that push and pull the mirror into the right shape. The sensors measure the atmosphere thousands of times per second. And the computers. They calculate the corrections faster than a human eye can blink. The result is astonishing. With adaptive optics, ground-based telescopes can see almost as clearly as space telescopes. Stars that used to flicker and blur now appear sharp, steady, frozen. Scintillation, the thing that plagued astronomers for centuries, has been mostly defeated. But here's the irony. We spent centuries trying to get rid of the flicker, trying to see stars as they really are without the shimmer. And yet for most of us, for everyone not using a telescope, the flicker is still there. Because we don't have adaptive optics in our eyes. We don't have mirrors that adjust. We just have the atmosphere and the stars and the ancient dance between them. And maybe that's okay. Because the flicker, the scintillation, the shimmer, it's part of the experience. Part of what makes looking up feel magical. We named it. We measured it. We learned how to fix it. But we didn't erase it. We can't. Not for everyone. The stars still flicker, and they always will. Here's something interesting. Different stars scintillate differently. Bright stars flicker less than dim stars. Why? Because bright stars send more photons, more particles of light toward your eye every second. And when you're averaging over thousands of photons, the fluctuations smooth out. Dim stars send fewer photons. So each individual flicker is more noticeable. Blue stars flicker more than red stars. Why? Because blue light has a shorter wavelength, and shorter wavelengths are refracted more strongly than longer wavelengths. So blue light bends more as it passes through the atmosphere. And more bending means more scintillation. That's why stars near the horizon sometimes seem to change color, flickering between red and blue and white. The atmosphere is splitting the light into its component colors, and those colors are scintillating at different rates. It's a prism, a natural prism made of air. Here's a question. Have you ever watched a single star for a long time, really watched it without looking away? If you have, you've probably noticed it doesn't just flicker randomly. There's a rhythm, a pattern, almost like it's breathing. That's scintillation. That's the atmosphere pulsing, moving, bending light in waves. Now let's talk about planets again. We've said planets don't scintillate as much as stars, and that's true. But they do scintillate a little. Mars, when it's far from Earth, appears small enough that it scintillates faintly. Not like a star, but enough to notice if you're paying attention. Venus, when it's very low on the horizon, scintillates too. Not because it's far, but because the light is passing through so much atmosphere. Even the moon scintillates. Just barely. If you look at the edge of the moon with a telescope on a turbulent night, you'll see the edge ripple, shimmer, wave. That's scintillation. That's the atmosphere distorting everything, even something as close and bright as the moon. Nothing escapes it. Nothing arrives untouched. So here's what we've learned. Scintillation is real. It's measurable. It's understood. But understanding it didn't make it less beautiful. We know it's caused by turbulence. We know it's refraction. We know it's the atmosphere bending light, making stars tremble. And yet when you go outside and look up, when you see a star flicker in the dark, it still feels like magic. Because knowing how something works doesn't erase the wonder. It just adds layers. You're not just seeing a star. You're seeing a star through 100 kilometers of churning air. Through invisible currents, through micro-eddies, through a storm too small to feel. You're seeing time-light that traveled for years, for centuries, just to reach you. You're seeing physics, refraction, turbulence, the bending of light through a lens made of gas. And you're seeing beauty, the shimmer, the spark, the scintillation, all at once. We named it. We measured it. We learned to correct for it. But we didn't tame it. And maybe we never will. Because the flicker isn't a problem. It's a reminder. A reminder that we're standing at the bottom of an ocean looking up at fires burning in the void. A reminder that light, even light, that traveled forever still bends when it touches home. But if the atmosphere is the lens constantly shifting, constantly bending light, then where you stand matters too. Because the higher you climb, the thinner the air, and the thinner the air, the stiller the stars. That's where we're headed next, into elevation, into perspective, into the places where the sky begins to quiet. If you want to see stars without the shimmer, you have to climb. Not metaphorically, literally. You have to leave the thick air behind. You have to rise above the turbulence, above the warmth, above the breath of the planet. Because where you stand changes everything. The stars don't move. The light doesn't change. But the air between you and them, that air is different at sea level than it is on a mountain. Different in a city than in a desert. Different at the equator than at the poles. And those differences, those small shifts in elevation, in location, in geography, completely change how stars flicker. We've been talking about the atmosphere as if it's the same everywhere, but it's not. The air above a beach in Florida is nothing like the air above a peak in the Andes, and the stars seen from those two places shimmer in completely different ways. So let's climb. Let's move. Let's see what happens when you change your perspective, not just where you look, but where you look from. Let's start with something you've probably experienced. You're standing outside looking at the stars, and you notice some stars flicker wildly. Others barely move at all. What's the difference? Position. A star directly overhead at the zenith flickers much less than a star near the horizon. Why? Because of the path the light takes. When you look straight up, the light from that star is passing through the atmosphere at the shortest possible distance. It's traveling straight down through about 100 kilometers of air before reaching your eyes. But when you look at a star near the horizon, the light is coming in at a steep angle. It's not traveling straight down anymore. It's traveling horizontally through much more atmosphere. How much more? At the horizon, starlight passes through about 38 times more atmosphere than it does at the zenith. 38 times. That's not a small difference. That's a massive difference. Imagine you're looking through a window. If you look straight through the glass perpendicular, you see clearly. The glass is thin. The distortion is minimal. But if you tilt your head and look through the glass at a steep angle, the view warps. You see reflections. Colors shift. The glass, which seemed clear before now, bends everything. The atmosphere works the same way. When light comes straight down, it passes through a relatively thin layer of air. The distortion is small. But when light comes in at an angle, when it grazes through the atmosphere almost parallel to the Earth's surface, it passes through layer after layer after layer of air, and each layer bends the light, again, and again, and again. The result, stars near the horizon flicker like crazy. But it's not just flickering, it's color. If you've ever watched a star near the horizon, really watched it, you've probably noticed something strange. It changes color. One moment it's white, the next it's red, then blue, then red again. It seems to pulse through the spectrum, cycling through colors faster than seems possible. That's called chromatic scintillation, and it's caused by the same thing that makes prisms work. Different colors of light bend differently when they pass through air. Red light with its longer wavelength bends less. Blue light with its shorter wavelength bends more. So when starlight passes through the turbulent atmosphere at a steep angle, the red and blue components of the light get separated, refracted in slightly different directions. And because the atmosphere is constantly shifting, those colors flicker in and out of view. Your eye sees red, then blue, then red again. It's the same light, the same star, but the atmosphere is splitting it apart like a prism made of wind. This is why the sun looks red at sunset. During the day when the sun is overhead, it looks white or maybe slightly yellow. But at sunset, when the sun is at the horizon, it turns orange, then red, then deep blood red. That's not because the sun is changing. It's because the light is traveling through so much atmosphere that the blue wavelengths are scattered away, and only the red wavelengths make it through. The same thing happens with stars. But because stars are so much dimmer, the effect is more subtle. Instead of the whole star turning red, it just flickers between colors. A tiny prism, a tiny rainbow, trembling in the dark. So if position matters, if looking straight up is better than looking at the horizon, then the next question is obvious. What if you go higher? What if you climb a mountain? What if you get above some of the atmosphere? The answer: the stars steady. The higher you climb, the less atmosphere there is above you. And the less atmosphere there is, the less turbulence, the less bending, the less scintillation. At sea level, you're at the bottom of the atmospheric ocean. The air is thick, heavy, full of moisture. But at 3,000 meters, 4,000 meters, the air is thin, dry, cold, and the stars. The stars begin to calm. This is why astronomers build observatories on mountaintops. Not just because it's dark up there, not just because it's far from cities, but because the atmosphere is thinner. Mauna Kea in Hawaii sits at 4,205 meters above sea level. About 40% of the Earth's atmosphere is below it. The Atacama Desert in Chile, home to some of the world's most powerful telescopes, sits at 5,000 meters. Over half the atmosphere is below it. At those altitudes, the air is so thin you can barely breathe. Visitors get altitude sickness, headaches, dizziness, nausea. But the stars are steady, clear, sharp. The seeing the metric astronomers use to measure atmospheric distortion is often better than 0.5 arcseconds. That's almost perfect. From sea level, seeing is typically 2 or 3 arcseconds. From a mountain, it's 5 times better. But it's not just about altitude. It's about location. Some places on Earth have naturally calm atmospheres. Some places don't. Deserts, for instance, are excellent for stargazing. Not just because they're dark, but because they're dry. Water vapor in the air increases turbulence. It adds another layer of density variation, another source of refraction. But in a desert, the air is bone dry. There's almost no moisture. And without moisture, the atmosphere is more stable. That's why the Atacama Desert is one of the best places on Earth to observe the stars. It's high dry and incredibly stable. The stars barely flicker at all. Islands are good too, but for a different reason. On an island, especially a remote island, the air flows smoothly over the ocean before reaching land. Ocean air is stable. It doesn't have the temperature variations you get over land. So observatories are built on islands like La Palma in the Canary Islands or Mauna Kea in Hawaii. The air flowing in from the ocean is steady, predictable calm. The stars seen from these islands shimmer less than they do almost anywhere else on Earth. But here's the sad truth. Most of us don't live on mountaintops. We don't live in deserts or on remote islands. We live in cities, near sea level, surrounded by buildings, roads, heat. And cities are terrible for stargazing. Not just because of light pollution, though, that's a huge problem, but because of heat. Cities are hot. Roads, buildings, parking lots, they absorb heat all day and radiate it back at night. That heat creates thermals, rising columns of warm air, turbulence, and turbulence makes stars flicker. So even if you could somehow block out all the city lights, even if you could see the stars clearly, they'd still shimmer wildly. Because the air above a city is chaotic. Here's a comparison. Stand in the middle of a city on a summer night. Look up. Find a bright star, Vega maybe, or Arcturus. Watch it. Really watch it. It flickers rapidly, almost violently. The light seems to dance, to pulse, to shift. Now drive out of the city. Go to the countryside. Find a dark field far from roads, far from buildings. Look at the same star. It's calmer, steadier. The flicker is slower, gentler, softer. Now imagine climbing a mountain. Imagine going to 4,000 meters. Imagine standing in the Atacama Desert under the clearest sky on Earth. Look at that same star again. It's almost still. Almost perfect. The star hasn't changed. You're still looking at the same light from the same source traveling the same distance. But the air is different. And that difference is everything. Here's something most people don't realize. Humidity doesn't just affect how stars flicker. It affects how many stars you can see. In a humid place near the coast, in a rainforest, in a swamp, the air is full of water vapor. And water vapor scatters light. Not just starlight. All light. So even if there's no light pollution, even if the sky is technically dark, the moisture in the air creates a kind of haze, a glow, a softness, and that glow makes faint stars disappear. But in a dry place, in a desert, on a high plateau, where the air is thin and bone dry, the sky is black, truly black. And faint stars you could never see from a humid place, suddenly become visible. It's not that there are more stars. It's that the air is clear enough to let their light through. Have you ever been somewhere, maybe on a trip, maybe on a hike, where the stars looked different than they do at home? Brighter, steadier, more numerous. That's not your imagination. That's the air. That's the atmosphere, quieter, thinner, letting the universe through. Now let's talk about latitude. The closer you are to the equator, the more atmosphere you're looking through. Why? Because the Earth bulges at the equator. The atmosphere is thicker there, about 8 kilometers thicker than at the poles. So if you're standing at the equator and looking at the stars, you're looking through more air than someone standing at the North Pole. More air means more turbulence, more scintillation. But there's a trade-off. At the equator, you can see both the northern and southern skies. You have access to more stars, more constellations, more of the galaxy. At the poles, the atmosphere is thinner, the stars are steadier, but you only see half the sky. So where's the best place to be? Somewhere in between. Somewhere with access to a wide view of the sky, but also with thin, stable air. That's why observatories cluster around 20 to 30 degrees latitude. Chile, Hawaii, the Canary Islands. It's the sweet spot. The place where the atmosphere is calm enough and the sky is wide enough. But even in the best locations, stars still flicker. Even on Mauna Kea, even in the Atacama, even with adaptive optics correcting for turbulence, stars still shimmer. Just a little. Because you can't escape the atmosphere entirely. Not unless you leave the planet. And that's exactly what we did. In 1990, the Hubble Space Telescope was launched into orbit. Not on a mountain, not in a desert, in space. 400 kilometers above the Earth, above the atmosphere, above the turbulence, above all of it. And for the first time, humanity saw stars without scintillation. No flicker, no shimmer, no chromatic aberration, just pure, unbroken light. Hubble's images are sharper than anything taken from the ground, not because Hubble is a bigger telescope, but because it doesn't have to look through air. It sees the universe directly, unfiltered, untouched. But here's the thing. We can't all go to space. We can't all orbit the Earth, floating in the void, looking at stars through vacuum. Most of us are stuck down here, at the bottom of the ocean, and that's okay. Because the flicker, the shimmer, the scintillation, it's not a flaw. It's proof. Proof that we live on a planet with an atmosphere, with air, with life. Dead worlds don't have scintillation. Mars barely has it. The moon doesn't have it at all. But Earth makes stars flicker. And maybe that's beautiful. So the next time you look up, think about where you're standing. Think about the air above you, thick or thin, dry or humid, calm or turbulent. Think about the elevation, the latitude, the geography. All of it matters. All of it shapes what you see. The stars are the same. But the view depends on where you stand. And maybe that's a reminder, perspective matters. Location matters. Where you are changes what you see. Not just in astronomy, in everything. But there's one more perspective we haven't explored yet. The strangest one. The one that lives inside you. Because the flicker isn't just in the stars or the air, it's also in your eyes, in your brain, in the way you hold light before letting it go. The flicker isn't just out there. It's in here too. In your eyes, in your brain, in the way you process light, hold it, interpret it, let it go. Because seeing isn't passive. It's not like opening a window and letting the world pour in. Seeing is active. It's construction. It's your brain taking fragments of light and building a story. And sometimes, more often than you'd think, that story includes things that aren't quite real. We've talked about the atmosphere, about turbulence, about refraction. All of that is real. All of that happens outside your body in the air, between you and the stars. But there's another layer, a quieter one, a stranger one. The layer that happens inside you. Let's start with something simple. Your eyes aren't cameras. Cameras capture an image instantly. Click. Done. The light hits the sensor and the picture is made. But your eyes take time. When light enters your eye, it hits the retina, a thin layer of cells at the back of your eye. Those cells convert light into electrical signals, and those signals travel to your brain. But the conversion isn't instant, and the signals don't travel instantly. There's a delay, a tiny delay, a fraction of a second. And during that delay, your brain is filling in the gaps. It's predicting what you're seeing. It's smoothing out the rough edges. It's making guesses. And sometimes those guesses are wrong. Here's an example you've probably experienced. You're looking at a star, a bright one, and you blink. For a split second, the star disappears. Your eyelid blocks the light. But when you open your eyes again, the star is still there. And it doesn't feel like it ever left. Why? Because your brain kept it there. Your brain remembered the star. It held on to the image even while your eyes were closed, and it seamlessly stitched the before and after together. You didn't notice the gap. You didn't feel the interruption. Your brain lied to you. Gently, helpfully, and you believed it. Now let's talk about flicker. When a star flickers, when its light wobbles, brightens, dims, it's not flickering randomly. It's flickering fast, very fast. sometimes several times per second. But your eyes can't keep up with that. Your brain processes visual information at about 10 to 12 frames per second, maybe 15 if you're really paying attention. Anything faster than that, your brain smooths it out, averages it, blurs it together. It's called persistence of vision. Your brain holds on to an image for about 1/10 of a second after the light is gone. And during that time, if new light arrives, your brain blends the two images together. That's how movies work. That's how animation works. A movie plays at 24 frames per second. But you don't see 24 separate images. You see one continuous flowing motion, because your brain is filling in the spaces between the frames. The same thing happens with stars. When a star flickers 5 times in 1 second, you don't see 5 distinct flickers. You see one smooth, trembling glow. Your brain is averaging the light, smoothing it out, making it feel continuous even though it's not. So the flicker you see, it's not exactly the flicker that's happening. It's your brain's interpretation of the flicker. It's softer, slower, more dreamlike. Here's where it gets strange. Your eyes don't see the entire image at once. You think they do. It feels like they do. But they don't. Your eyes have a small area in the center, the fovea, where vision is sharp. That's where you see detail, color clarity. But the edges of your vision, the periphery, it's blurry. Low resolution. Almost useless. Your brain hides this from you. It takes the sharp image from the center and the blurry image from the edges, and it stitches them together into one seamless picture. It makes you think you're seeing everything clearly all at once. But you're not. You're only seeing clearly where you're looking. Everything else your brain is guessing. This matters for stars. If you stare directly at a faint star, it often disappears. You look right at it, and it vanishes. But if you look slightly to the side, if you use your peripheral vision, the star comes back. Why? Because the center of your eye, the fovea, is packed with cells called cones. Cones are great for color and detail, but they're terrible in low light. The edges of your eye, though, they're packed with cells called rods. Rods are useless for color, but they're excellent in low light. So if you want to see a faint star, you have to not look at it. You have to look away. Astronomers call this averted vision, and it's one of the oldest tricks in stargazing. Ancient sailors knew it. Medieval monks knew it. Anyone who spent enough time looking at the night sky figured it out eventually. Don't stare. Glance. But here's the paradox. When you use averted vision, when you see a star out of the corner of your eye, it flickers more. Why? Because your peripheral vision is faster. It's more sensitive to motion, to change, to flicker. Your peripheral vision evolved to detect threats, movement, something darting in the shadows. So it picks up on rapid changes in light changes your central vision would smooth over. That means a star seen out of the corner of your eye appears to flicker wildly. But when you turn to look at it directly, it steadies. Not because the star changed, but because your eye changed. Your brain changed the way it's interpreting the light. There's another phenomenon, a stranger one. Sometimes when you're staring at a star, it starts to move, not flicker, move. It drifts, slowly, across the sky. You watch it for a few seconds, and you swear it's shifting left, then right, then up. But it's not moving. The star is perfectly still. So what's happening? It's called the autokinetic effect. When you stare at a single point of light in complete darkness with no reference points, No frame, no context. Your brain loses track of where it is. Your eyes make tiny involuntary movements called microsaccades. Little jitters, little shifts. Normally, your brain compensates for these movements. It knows your eyes are moving, so it adjusts the image to keep it stable. But when there's only one point of light with nothing else to anchor it, your brain gets confused. It thinks the light is moving when really your eyes are. So the star appears to drift, to wander, to float across the sky. It's an illusion, a trick of perception. But it feels real. Pilots know about this, especially pilots flying at night over the ocean. They're trained to never fixate on a single light. Because if they do, the light will seem to move. And they'll think they're tilting, turning, losing altitude. It's caused crashes. It's caused deaths. Because the brain, given just one point of reference, will lie. Here's a question. Have you ever stared at a star so long that it seemed to pulse or drift or change in ways you couldn't explain? That's not the star. That's you. That's your brain trying to make sense of something too small, too far, too faint. Now let's talk about something you've definitely experienced. Floaters, those little shapes that drift across your vision. Tiny dots, threads, squiggles. They're not in the world. They're in your eye. Floaters are small clumps of protein or cells suspended in the vitreous, the gel-like substance that fills your eyeball. They cast shadows on your retina, and those shadows look like moving shapes. Most of the time, you don't notice them. Your brain filters them out. But when you're looking at something bright and uniform like the sky, they become visible. And at night, when you're looking at stars, floaters can look like stars. You'll see a faint dot drift across your vision. You'll think it's a satellite, a shooting star, a UFO. But it's not. It's just a piece of protein floating inside your eye. There's also something called phosphinies. Phosphinies are flashes of light that you see even when no light is entering your eye. They're caused by pressure on the retina or by random firing of the neurons in your visual system. If you close your eyes and press gently on your eyelids, you'll see phosphines. Flashes, patterns, shapes. They're not real. They're just your visual system misfiring, creating the sensation of light where none exists. And sometimes late at night, when you're staring at the stars in total darkness, you'll see a flash, a brief spark of light. You'll think it's a meteor, a satellite, something out there. But sometimes it's just a phosphine, just your brain flickering on its own. So here's the truth. Not everything you see in the night sky is real. Some of it is the atmosphere. Some of it is refraction. Some of it is turbulence. But some of it is you. Your eyes, your brain, your nervous system constructing a version of reality that isn't quite accurate. And that's okay. Because seeing has never been about perfect accuracy. It's about survival. It's about making quick decisions with incomplete information. Your ancestors didn't need to see the stars perfectly. They just needed to see them well enough to navigate, to track time, to tell stories. And so your eyes evolved to be good enough. Not perfect, just good enough. But here's the beautiful part. Even though your eyes lie, even though your brain fills in gaps and smooths out flickers and makes stars drift when they're standing still, it still works. You still see the stars. You still feel their light. You still look up and feel small and connected and alive. Because the flicker, the shimmer, the slight unreality of it all, that's part of the magic. Your eyes aren't telescopes. They're not cameras. They're not scientific instruments. They're storytellers. They take fragments of light, ancient, bent trembling, and they turn it into experience, into wonder, into something that makes you stop and look up and forget for a moment about everything else. So the next time you look at a star, remember you're not seeing it as it is. You're seeing it as your brain has decided it should be. Smoothed, averaged, interpreted, constructed. And that's okay, because the star is still there. The light is still real. And the story your eyes are telling you, flickering, drifting, pulsing in the dark, that's real too. Ancient sailors used stars to navigate. They didn't need perfect vision. They didn't need to see the stars exactly as they were. They just needed to see them well enough to find their way home. And they did. For thousands of years, across oceans, under skies full of flickering, trembling, imperfect light, they found their way. Because the stars even distorted, even filtered through air and eye and brain, they're still enough. They're still there. Still guiding. Still shining. Still holding the night together. But all of this, the atmosphere, the turbulence, the eye, the brain, all of it assumes one thing: that we're standing on Earth, that we're looking up through air, that we're wrapped in this blanket of gas that bends and hides and distorts. So what happens when you leave? When you step outside the atmosphere into the void, where there's nothing between you and the stars? Imagine this: you're floating, weightless, silent. Below you, the earth curves blue and white, wrapped in its atmosphere like a veil. Above you, darkness, pure, absolute, endless. And in that darkness, stars, thousands of them, tens of thousands, more than you've ever seen from the ground. And they don't flicker, not even once. They hang there frozen perfect, like diamonds pressed into black velvet. This is what astronauts see. This is what space looks like. And it changes everything. We've spent this whole journey talking about why stars flicker, about the atmosphere, the turbulence, the refraction, about the air between us and them bending light, making distant suns tremble. But now we're going to talk about what happens when you remove the air, when you leave the planet, when you step outside the ocean and see the universe as it really is. Because out there, beyond the atmosphere, stars don't shimmer. They don't dance. They don't breathe. They just shine. Steady, still, eternal. Let's go back to 1969, Apollo 11, 3 men in a tiny capsule hurtling toward the moon. Neil Armstrong, Buzz Aldrin, Michael Collins. For 3 days, they traveled through the void. And every night, or what passed for night in space, they looked out the window. And they saw stars. But not like they'd ever seen them before. On Earth, even on the clearest night, stars flicker. They shimmer. They pulse. But in space, the stars were hard, sharp, unwavering. Buzz Aldrin described it later. He said the stars looked unreal, like they'd been painted onto a backdrop, like they weren't moving, weren't alive. They didn't twinkle. And without the twinkle, they felt strange, almost fake. Because we're so used to the flicker. We're so used to stars that tremble, that when we see them perfectly still, they don't feel right. Here's why stars don't flicker in space. There's no atmosphere. That's it. That's the whole answer. On Earth, stars flicker because their light passes through 100 kilometers of churning air. The air bends the light constantly, unpredictably. But in space, there's no air, no gas, no molecules to bend the light. Just vacuum. And in a vacuum, light travels in perfect straight lines. No wobble, no distortion, no change. So the stars, those distant suns burning trillions of miles away, appear exactly as they are. Steady, still, frozen in the dark. Astronauts on the International Space Station see this every day, or every 90 minutes technically. That's how long it takes the ISS to orbit the Earth. Every 90 minutes they pass from daylight into darkness. And when they do, the stars come out. And they don't flicker. Scott Kelly, who spent a year on the ISS, said the stars were one of the strangest things to get used to. On Earth, you glance at the sky and the stars feel alive. They shimmer, they move. But in space, you look out the window and the stars just stare back, unblinking, unmoving, like they're watching you. But here's something people don't realize. In space, stars are harder to see. Wait, what? You'd think it would be the opposite. No atmosphere, no light pollution, nothing in the way. Shouldn't stars be easier to see? Not necessarily, because space is bright. Not the darkness of space itself, but the sunlight. When the sun is in view, when the ISS is on the day side of the Earth, the sunlight is blinding, impossibly bright. There's no atmosphere to soften it, no air to scatter it. Just pure, direct, unfiltered sunlight. And in that light, stars disappear. Not because they're not there, but because the contrast is too great. The sun overwhelms everything. It's like trying to see stars at noon on Earth. You can't. The sky is too bright. In space, the same thing happens. When the sun is up, the stars vanish. But when the sun sets, when the ISS passes into the Earth's shadow, the stars come back. And they're sharp, clear, perfect. Let's go farther. Let's go to the moon. In July 1969, Neil Armstrong and Buzz Aldrin became the first humans to walk on another world. And when they looked up, they saw something no human had ever seen before: stars in a black sky. In the middle of the day. On Earth, the sky is blue during the day because the atmosphere scatters sunlight. That scattering fills the sky with light, making stars invisible. But the moon has no atmosphere, no air, no scattering. So even with the sun blazing overhead, the sky stays black. And in that blackness, stars, or at least they should have been visible. But here's the problem. The moon's surface is bright, incredibly bright. The lunar soil, the regolith, reflects sunlight intensely, and in the glare of that reflected light, stars are hard to see. It's the same problem astronauts face on the ISS. The contrast is too great. So during the Apollo missions, astronauts didn't spend much time looking at stars. They were too busy, too focused on not dying. But at night, during the lunar night, when the sun was below the horizon, the stars came out. And they were stunning. Brighter than on Earth. Sharper, more numerous, because there was no atmosphere, no air, no interference. Just light traveling unbroken across the void, finally reaching eyes that could see it clearly. Here's a common misconception. People look at photos from the Apollo missions and say, "Where are the stars? There should be stars in the sky. This is proof the moon landing was fake." But that's not how cameras work. When you take a photo of a bright subject like an astronaut in a white spacesuit, standing on bright lunar soil with the sun blazing, you have to use a fast shutter speed. A fast shutter speed lets in very little light, just enough to capture the bright subject. But stars are faint. To capture stars, you need a long exposure, a slow shutter speed. You can't do both at once. So in every Apollo photo, the stars are there, They're just too faint to show up. But the astronauts saw them. Every single one of them reported seeing stars when the conditions were right. And they said the same thing: the stars didn't flicker. And it felt wrong. Let's talk about Mars. Mars has an atmosphere, but it's thin, very thin. About 1% the density of Earth's atmosphere. That's almost nothing. It's barely there. So do stars flicker on Mars a little, but not much. The Mars rovers Spirit, Opportunity, Curiosity, Perseverance have all taken pictures of the night sky. And in those pictures, stars appear steady, almost perfectly still. There's just not enough atmosphere to create significant turbulence, not enough air to bend the light. So stars on Mars look more like stars in space than stars on Earth. But here's where it gets interesting. On Mars, you can see Earth. From the surface of Mars, Earth is visible as a bright blue star. Not a planet, a star. Because Earth is far enough away that it appears as a single point of light. And that light, it doesn't flicker. Because Mars's atmosphere is too thin to create the kind of turbulence that makes stars shimmer. So if you were standing on Mars looking up at Earth, you'd see your home, the entire planet, with all its oceans and continents, and life as a single, steady blue dot. Not flickering, not trembling, just glowing, still and silent in the dark. Now let's talk about a place with no atmosphere at all. Mercury. Mercury is the closest planet to the Sun. It's small, rocky, heavily cratered, and it has no atmosphere. None. So what do stars look like from Mercury perfect? Absolutely perfectly still. No flicker, no shimmer, no distortion, just pure, unbroken light. If you could stand on Mercury during the brief moments when the sun wasn't frying you alive, you'd see the sharpest, clearest stars in the solar system. No air to bend them, no turbulence to shake them. Just the universe exactly as it is. But here's the trade-off: atmospheres make stars flicker, but they also make life possible. Mars has almost no atmosphere. Mercury has none. The Moon has none. And none of those places can support life. Because atmospheres do more than just bend light. They trap heat. They provide oxygen. They shield the surface from radiation. They make planets habitable. So yes, atmospheres distort the view. They hide the stars. They make the universe shimmer and blur. But they also let you stand there breathing, looking up, wondering. Without an atmosphere, you'd see the stars perfectly, but you wouldn't be alive to see them. Here's a question. If you could choose perfect, unflickering stars, but no air to breathe, or flickering, shimmering stars, but the warmth and breath of home, which would you pick? Astronauts talk about this a lot. When they come back from space, they say the same thing. The stars in space are beautiful, but they're cold, distant, lifeless. The stars on Earth, flickering, trembling, imperfect, feel warmer, more alive. Because the flicker is a reminder that you're standing on a living planet, that there's air around you, moving, breathing, that you're home. Chris Hadfield, who spent months on the ISS, said this: "In space, the stars don't twinkle." And I missed that. I missed the way they shimmer on Earth. Because the shimmer means there's air, and air means life. So here's what we've learned. Stars don't flicker in space. They don't flicker on the Moon. They barely flicker on Mars. Because flickering requires an atmosphere. It requires air turbulence, refraction, and most places in the universe don't have that. Most places are airless, lifeless, silent, but Earth has air, Earth has life. And because of that, our stars flicker, they shimmer, they dance, they tremble in the dark. And maybe that's not a flaw. Maybe that's the most beautiful thing about them. Because the flicker, the shimmer, it's proof. Proof that we live on a planet with weather, with wind, with breath. Proof that we're not floating in the void surrounded by silence. We're standing on a world that's alive. And the stars filtered through that life reflect it back to us. They don't just show us the universe. They show us home. So the next time you look up and see a star flicker, remember that flicker is a gift. It means you're standing on a planet with an atmosphere. A planet that protects you, that shelters you, that lets you breathe. The stars in space are perfect, but they're cold. The stars on Earth are imperfect, but they're warm. And warmth in the end is what matters. We've traveled far from the surface of the Earth, through layers of air into the mechanics of sight, and finally beyond the atmosphere altogether. We've learned why stars flicker how we see them, and what happens when the air disappears. But now, as the night deepens and the journey nears its end, there's one last thing to understand what all of this means. Not scientifically, but quietly, softly, in the space between knowing and feeling. We've walked through light and air tonight, through time, through distance, through the invisible currents that make stars tremble. And now here at the end, maybe you're lying down. Maybe your eyes are heavy. Maybe the world has grown quieter, softer, smaller. That's good. Because this last part isn't about learning anymore. It's about feeling, about letting the science settle into something deeper, about understanding not with your mind, but with the part of you that looks up at the night sky and feels something. Wonder maybe, or smallness, or connection. All of it. None of it? Just something. Let's go back to the beginning. We started with a question. Why do stars flicker? And now you know. You know it's not the stars. It's the air, the atmosphere, the invisible ocean we live in, constantly moving, constantly bending light. You know it's turbulence, thermals, rising, jet streams, flowing, micro eddies, spinning. You know it's refraction light, changing speed, changing direction as it crosses from one density to another. You know it's perspective, where you stand, how high you climb, how much air is between you and the sky. You know it's your eyes smoothing, averaging, filling in the gaps, constructing a version of reality that's close enough. And you know it's the atmosphere itself, proof that you live on a planet with air, with weather, with life. But here's the thing. Knowing doesn't erase the mystery. Even now, after everything we've talked about, when you go outside and look up, the stars still flicker. And it still feels like magic. Because knowledge doesn't replace wonder. It just adds layers. You can know exactly why stars shimmer down to the photon, down to the molecule, and still feel your chest tighten when you see them. Still feel small. Still feel connected. Still feel like you're part of something vast and ancient and impossible to name. That's the gift of science. It doesn't take away the beauty. It deepens it. Think about the light for a moment. The light touching your eyes right now if you're looking at a star traveled for years, maybe centuries. It crossed distances so vast that even light moving at the fastest speed possible takes lifetimes to arrive. And it arrived almost perfectly. Almost. It traveled through the vacuum of space without wavering, without fading, without breaking. But in the last 100 kilometers, the very last stretch, it bent. It wobbled. It trembled. It flickered. Not because the journey broke it, but because it finally touched something. It touched air. It touched home. And that touch, that final interaction, is what you see. The shimmer isn't a flaw. It's proof of arrival. Here's something to think about as you drift towards sleep. Every photon of starlight that reaches you has traveled alone. Light doesn't travel in groups. It doesn't hold hands with other photons. It moves individually, one particle at a time. And yet somehow, billions of photons arrive every second, perfectly coordinated, perfectly timed, creating the image of a star in your mind. Each one traveling separately, each one crossing the void alone, and all of them arriving together. Just for you. That's what you're seeing when you look up. Not just light, but a kind of impossible choreography. Billions of solo journeys ending in the same place at the same time, creating something whole. Ancient humans didn't know about photons. They didn't know about refraction or turbulence or adaptive optics. But they knew the stars flickered, and they built entire mythologies around it. The Greeks thought the shimmer was divine breath. The Romans saw it as the gods speaking. Indigenous cultures across the world saw flickering stars as ancestors watching, communicating, guiding. They were wrong about the mechanism, but they weren't wrong about the feeling. Because the flicker does feel like communication, like the stars are alive somehow, like they're reaching out. And in a way they are. Because starlight is the only way the universe can touch you directly. You can't touch a star. You can't hear it. You can't smell it or taste it. But you can see it. You can let its light enter your eye, cross your retina, become a signal in your brain. The stars are 4 light years away, 640 light years away, thousands of light years away. But their light, ancient, patient, impossibly fragile finds you. And when it does, it flickers. Because it's passing through the air that keeps you alive. There's a poet, I can't remember who said this: the stars are not indifferent. They're just very, very far away. And maybe that's true. Maybe the flicker is the star's way of saying, I see you. I'm here. I made it. Or maybe the flicker is just physics. Just air bending light doing what air does. Both can be true. Science and poetry. Fact and feeling. You don't have to choose. Here's something Carl Sagan said back in 1980 in his series. Cosmos, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. It's one of the most famous lines in science, and it's true. The atoms in your body, every single one, were forged in the core of a star billions of years ago. That star lived, it burned, and then it died, exploding, scattering its atoms across the void. And those atoms drifted, for eons, through space, through dust clouds, through the formation of the solar system, until eventually, impossibly, they came together. They became the earth, the oceans, the air, and you. So when you look up at the stars, you're not just looking at distant suns. You're looking at your ancestors, your origin, the furnaces that made you possible, the flicker you see. That's family calling across the dark. And maybe that's why the shimmer feels so important. Why it matters, even though it's just refraction. Because on some level, some deep, wordless level, we know. We know we're connected to the stars. Not metaphorically, literally. We're made of the same substance, the same light, the same dust. And when starlight flickers through the air, when it bends and trembles before reaching your eyes, it's completing a circle. A circle that started billions of years ago in the heart of a dying star, and ends here, now, in you. Have you ever felt that strange sense of connection when you look at the stars, like you're remembering something you never learned? That's not mysticism. That's chemistry. That's physics. That's the atoms in your body recognizing their origin. So here we are, at the end. You know why stars flicker now. You know the science, the history, the mechanics. But more than that, I hope you know the feeling. The feeling of standing at the bottom of an invisible ocean, looking up at fires burning trillions of miles away. The feeling of seeing light that's older than you, older than civilization, older than language. The feeling of watching that light tremble just before it reaches you because it's passing through the air that keeps you alive. The stars don't flicker because they're broken. They flicker because you're home. Because you live on a planet with an atmosphere, with weather, with life. And that atmosphere, the very thing that hides the stars, that blurs them, that makes them shimmer, is also the thing that lets you stand there breathing, watching, wondering. You can't have it both ways. You can't have perfect, unflickering stars and also have air to breathe. The flicker is the cost, and the gift. It's the price of living on a planet that's alive. And it's the proof that you're not alone in the void. You're standing on a world, wrapped in gas, protected, held, and the stars filtered through that protection shimmer just for you. So tonight, as you close your eyes, as you drift toward sleep, maybe think about this. Somewhere above you, right now, starlight is bending. It's passing through invisible currents, through pockets of warm and cool air, through the breath of the planet. And it's trembling, not because it's weak, but because it's almost home. Because after traveling for years, for centuries, across distances too vast to imagine, it's finally touching something. Finally arriving. And that arrival, that shimmer, that's the last dance. The final motion before stillness. Before the light enters your eye and becomes memory. Becomes feeling, becomes wonder. We've walked through neurons and dreams, through light and silence tonight. Through centuries of questions and decades of answers. Through turbulence and refraction, through elevations and perspectives, through space and time. And maybe knowledge was never meant to be kept, only felt for a moment. Just long enough to change the way you see. The next time you look up, and you will look up because now you'll notice. When you see a star flicker, you'll know it's not the star. It's the air. It's home. And that flicker, that shimmer, that's the universe whispering through the only language it knows. Light, bent by time, softened by distance, trembling in the dark. Sleep well. Dream gently. And if you wake in the night and the sky is clear, look up. Let the stars flicker just for you, because they've traveled so far, and you were here to see them. That's enough. That's everything. Good night. Thank you for being here, for listening, for drifting through this quiet journey with me. If these slow nights bring you comfort, I'll be here again soon with another story, another question, another soft unraveling of the universe. Until then, rest easy and let the stars keep watch. They've been doing it for billions of years. They're not going to stop now.